we'd like to introduce our next speaker, who's Professor Phil Diamond. He's going to be telling us about the SKA project. So Professor Diamond is the Director General of the SKA, where he's been in his role since 2012. So he must have seen some exciting developments over that time as we prepare for the SKA. And we look forward to hearing about it. Thanks, Phil.
Thank you. Can you hear me clearly?
Yes.
Good. Well, thank you very much for the invitation to talk at this fantastic event. I'm going to describe to you the current status of the Square Kilometre Array, an observatory which we hope will tackle some of the major questions in science in the 21st century. But first of all, I would like to, I'd like to extend my congratulations to the SAAO on its bicentenary. And I'm speaking from the Jodrell Bank Observatory, which hosts the headquarters of the SKA. So from one observatory to another, very, very happy birthday to our colleagues in South Africa. And I'm speaking about a subject that is only 90 years old. The first radio astronomy observations were performed in 1931. Of course, SAAO has been in existence for twice as long as that, which is truly impressive. If we look at 21st century astronomy, the mega facilities that are either operational or under construction are truly impressive. In fact, I often say when I show this slide that I really do wish I was 30 years younger, because the facilities and the capabilities that will be available to the young generation of astronomers is really awesome, to use a word our colleagues across the Atlantic often use. And you can see some of the major facilities pictured there on this slide, with SKA being one of the cornerstone observatories for the 21st century, providing the capabilities in the radio regime. So what science will the SKA tackle? Well, it's a huge range of science, covering almost the entire history of the universe, from fundamental physics through testing general relativity, exploring gravitational waves, all the way through to potentially the origins of life, and many, many things in between. I don't have time to cover more than a tiny fraction of the science case that SKA will open up. But I will touch on two particular items, but you can see the headline science here on the screen. And importantly, in designing a facility for the 21st century, one must be aware that there are many phenomena that will be brand new to us, that we have not yet discovered. And so a telescope for this time in humanity's life must be able to explore unknown discoveries as and when they are made. So looking back on what I'll talk about very briefly about two areas of science that the SKA will explore. And one is the dawn of the universe. So satellites like ESA's Planck mission, which operated up until 2013, had its precursors, Wilkinson microwave anisotropy probe and COBE before it, observed radio waves from the cosmic microwave background. And one of Planck's key results was this image that you see on the screen now, which is really a snapshot of what the universe looked like at 400,000 years old. But with the SKA, and through the study primarily of hydrogen, the most common element in the universe, we hope to be able to build on these fantastic results. So you can see there that this snapshot sits occupies that vertical line in this very compressed history of the 14 billion years of the universe, sitting there at about 400,000 years after the Big Bang. But there's a whole period of the Dark Ages, the epoch of reionization, when the first stars appeared, first supernova and black holes, when galaxies evolved. This is a period of the universe that is largely unexplored and is mysterious to us. But with the SKA and with modern complementary instruments, we'll begin to explore this in some detail. So one of the key science goals of the SKA is to use hydrogen, redshifted hydrogen, to make a movie of this period of the dawn of the universe, simulated in this little diagram that you see here. Now, our colleagues, theoretical astronomer colleagues, have simulated the sort of thing that we might see. And this is a particular simulation from colleagues at the University of Toronto, where what you see, this is a cube, of course, of a megaparsec scale cube, showing the so-called Swiss cheese effect, which is growing bubbles of ionized material, which sits in a sea of neutral hydrogen. And you can see how these bubbles grow into the sorts of structures that we do see now in the more recent epochs of the universe. So this is an evolution over about 1 billion years. And we do hope that the SKA will be able to produce real physical tomographic movies of this sort of evolution in the future. So that's one of the key science goals. A second, just picking another from the list of key science projects, is exploring the origins of life in the universe. So molecules, the spectral line emission from different molecules has been long known within radio astronomy and other wave bands. The Atacama Large Millimeter Array is doing some superb work in understanding the distribution, the dynamics, the evolution of different molecular species. There are over 200 molecular species that now exist. But one of the key goals of the SKA will be to search for some of the building blocks of life itself. Glycine, for example, one of the key goals of prebiotic astrochemistry. Discovery of glycine would be the first detection of an amino acid in space in the gas phase. And it would be very interesting to see how widespread this is in the universe, if it can be detected in protoplanetary systems or even in interstellar space. This is one of the key goals. Now, interestingly, one of the key emission lines of glycine sits within one of the bands that is potentially impacted by the satellite megaconstellations that were mentioned in a question to Evine a few moments ago. And of course, what we are talking to the satellite megaconstellation operators to minimize their impact on the SKA. And they can do that by directing their beams slightly away from our telescopes, so the noise does not overwhelm us as we make our observations. So if I can move on to the SKA Observatory itself. We are a global collaboration that's been in existence now for some years, designing, and next year we hope to start building and then operating the next generation radio astronomy observatory. A treaty has been signed to establish the SKA Observatory as only the second intergovernmental organization in astronomy in the world, the first being the long-established European Southern Observatory. So we're looking to set up the SKA Observatory as something like ESO, like CERN, like ESA. This is important for in an international organization sitting across 3 continents with a multi-decade-long lifetime. We have 15 countries engaged in the partnership at this time, and we're going to build 2 radio telescopes, one in South Africa and one in Australia. I'll describe them in a moment, with the global headquarters in the UK, where I'm sitting right now. But there will also be, as well as our data processing centers close to the telescopes, a global network of regional centers, which is delivering science-ready data to the end users. So our partner governments are working to provide the large amount of funding, close to 2 billion euros, that we will need for the next 10 years to cover the construction and the first 10 years of operations of the observatory. Now, it's interesting that 30 years ago this month, there was a paper given at a conference celebrating the 10th anniversary of the VLA, which was Peter Wilkinson talking about the hydrogen array. This was, Peter was pulling together discussions that had occurred amongst many colleagues over a couple of years, thinking about the next big thing. But I just put this up there because it was 30 years ago this month. And that tells you how long it takes to go from an early concept to the start of construction for these mega science facilities. It's a long haul. It's a very hard, very complicated thing to do. So what are we going to build? You see here 2 artists' images of what the 2 telescopes will look like. On the left, the low frequency telescope operating between 50 and 350 megahertz will consist of 512 stations, each of 256 low frequency dipoles that you see in the picture there. Actually, the picture in the foreground is a real image of the prototype system out in the Western Australian desert. So this will sit in Western Australia, about 600 kilometers north of Perth, in a very remote region of the Earth. Extremely radio quiet and protected by Australian national legislation in order to enable us to do our science. And then similarly in South Africa on the right there, you see an artist's impression of what SKA Mid will look like. And in fact, you can see some of the meerkat dishes, the slightly smaller dishes on the right-hand side. Meerkat, the 64 dishes of meerkat will be incorporated into SKA Mid. And SKA Mid will operate initially over the frequency range 350 megahertz to 15 gigahertz. Both will be interferometer arrays spread over tens of kilometers, 150 kilometers in the case of South Africa. Of course, this is only the start of our ambition for SKA. We do plan a second phase with up to 2,500 dishes across Southern Africa and potentially 1 million antennas spreading across Western Australia. We do have precursors. You'll be hearing tomorrow from Rob Adam about Meerkat, an immensely successful project, 64 dishes, which is now operational and delivering superb science results. Also, Hera, an experiment to explore the epoch of reionization, is under construction adjacent to Meerkat. And then in Australia, we have 2 precursors operational, the Australian SKA Pathfinder, ASCAP, and the Murchison Wide Field Array. All of the SKA will be run from the global headquarters based at Jodrell Bank in the UK. And that's actually the picture I see out of my window right now as I speak to you, the Lovell Telescope. Believe it or not, the sun is shining here just south of Manchester. The headquarters building that you see there is a new purpose-built building, which can hold approximately 150 people. And this is our beautiful council chamber and auditorium, which once COVID-19 hopefully has faded away from our consciousness, will once again act as a nexus for world radio astronomy. So the current status, I've mentioned we've got 15 countries at present. You see them colored blue in the world map there. The newest members to join, you see their flags on the right-hand side, with Switzerland being the most recent in May of this year. We have Japan and South Korea as observers within our governance bodies, and we are, of course, open and are talking to some other countries about potential membership. The treaty was signed at a ceremony in Rome in March of last year by 7 of the members. More will be joining later, but these 7 were ready at that time to sign the treaty. Those are the countries' flags that you see there. South Africa, of course, sitting there right next to the Italian minister. And I'm very pleased to say that the 5 countries here have now ratified the treaty. The most recent being the UK that passed its final hurdle just last week on the 14th of October, although there are still some administrative steps to complete. So this paves the way for the SKA Observatory, the intergovernmental organization, to come into existence in the very near future. We also have prototype SKA hardware on site. So this is the SKA dish prototype, which is a design that is evolved and learned from the Meerkat experience. This is funded by our German colleagues, Max Planck Gesellschaft, and it has been immensely useful for testing purposes. It's critical to have these prototypes on the ground. And similarly, as I showed a little earlier, we have a prototype SKA low station sitting in Western Australia, which has also been critical to learn and characterize the electrical properties of that station. Recently, we completed all of our major reviews, critical design review of the entire system, review of our operations plan, a cost review of the business enabling functions, that's human resources, finance, etc., required to support the observatory. And most pleasing to me, the major milestone of recent times was that our construction proposal and the plan to establish and deliver the observatory were endorsed on the 17th of September by the SKA board, and they will be passed on to the council of the observatory for its first meeting, hopefully in December. So that's the culmination of many years' work by many, many people around the world. Really fantastic result. Just very briefly, the hardware is in some sense a straightforward part of the SKA. We largely know how to build the hardware, although the scale that will be delivered is greater than has been done before. But the handling of the data is a significant and new challenge for us astronomers. So we'll be having huge amounts of data, terabits per second, flowing from the telescopes themselves into what we call central signal processors, massive banks of digital electronics. These are on the sites a few kilometers away from the telescopes themselves. The data will then be transmitted over several hundred kilometers of fiber to supercomputers, one in Perth and one in Cape Town. These are an integral part of the telescope. They will be doing real-time processing and imaging of the data as it real-time processing, calibration, and imaging of the data as it comes off the antennas and the dishes. So you must change the way you think about a telescope. The supercomputers are integral to the operation of the telescopes. And these will be massive supercomputers. If they were built today, they'd be in the top 5 fastest supercomputers in the world. So they will generate, when we're fully operational, about 700 petabytes per year. This will be transmitted over undersea fiber optic cables to what we call SKA regional centers, computing centers distributed around the globe, which will be the access point to the SKA data to our user community. But just to give you some idea of the scale that we're having to deal with, now these numbers are a little bit outdated, not the SKA number, of course, but the Facebook and Google numbers. I'm not quite sure what they are now. This is what they were a couple of years ago. But you can see the scale of the data that we're having to handle. Now, our data is much more constrained, consistent, and less chaotic than the data provided to Google and Facebook. One thing governments are interested when something like the SKA is funded is what might be the knock-on benefits, the impact to society that flows from their expensive investments. Well, we like to show this now in terms of the UN Sustainable Development Goals, which you see on the screen here. And the SKA is not going to solve any of these problems, but it is going to contribute to society in several areas shown here. And just a couple of examples. First of all, looking back over the previous impact of radio astronomy. And Clifford actually mentioned John O'Sullivan and the invention of Wi-Fi, which was one of the major impacts of astronomy. But there's medical imaging, there's the reliance of space navigation and GPS on the reference systems provided by very long baseline interferometry, movement of tectonic plates, low noise amplifiers, tracking of space probes, citizen science. This is something that Aveen also answered a question on. And then of interest in South Africa and Africa more generally, the excellent programs from DARA and DARA Big Data. I'm sure we'll hear about the Human Capital Development Program in South Africa, which has really been tremendous and something that when the SKA is in country, we wish to contribute to and support. And I've mentioned DARA, the development in Africa with radio astronomy, which I think has been very successful. So these are, I think, very positive developments. Another one is we are very keen, and in fact, we are insistent that our impact on the climate, on sustainability, be very positive. So we've made some innovative and deliberate design decisions to keep the power consumption low. And I'm very pleased that the final design is about half of what the original estimates gave us. But what you see here in the picture is a real photograph of the hybrid solar diesel power station that sits adjacent to ASCAP. SKA will need something about 3 times as large as that, but it is all part of our intention to maximize the use of renewable power on both of our sites. So this is a pledge that we give to the community that sustainable development is something we are very keen on. So finally, in terms of the timeline, I've mentioned the treaty signing. The major reviews have happened. COVID has intervened, but we had our construction proposal and establishment and development plan endorsed by the SKA board. Our next milestone is the formation of the observatory, which I'm expecting now in the coming weeks, not months, with the first SKA Observatory Council meeting convening hopefully in mid-December. I'm then hoping that the council will approve the start of construction and we can begin construction activity. Our target date is the 1st of July, 2021, so not long now. And then, of course, we have a construction program that will last about 7 years, with a science commissioning activity starting once we have significant hardware on the ground. So thank you very much for your attention. and if there's time for any questions, happy to take them.
Thank you so much for that great presentation. We're really excited for the SKA's coming. I speak as a theorist when I say that it's going to be challenging for the theorists, because now we'll actually be able to compare our simulations to real data, and that's always a bit hairy. Do we have any questions on Slido?
Yes, we have one question for you from Richard Sessions, who asks, will the SKA be able to be used as the receiver arm of a sensitive solar system radar with the transmitter somewhere else, bearing in mind the Earth's rotation?
Yes, there's nothing to stop that happening. In fact, other radio telescopes do that. Bistatic radar observations of planets, asteroids, things like that happen fairly regularly. So I see no reason, as long as it's within the frequency range in which we operate, that SKA can't do that as well.
Good. I'd like to ask you a little bit more about Meerkat and the SKA. So I gather Meerkat will be incorporated into phase 1 of the SKA. Can you say a little bit more about how that will work?
Yeah, well, I can. Rob Adam may discuss this tomorrow, but Meerkat is obviously becoming operational now with its own science program. We will be constructing SKA-1 alongside Meerkat, and we paid a lot of attention to how we can undertake construction activities without interfering with the scientific observations of Meerkat. So there's a lot of work that has been done and is ongoing to minimize any disruption. And then at an appropriate point, which is a few years hence, when we have at least as many antennas on the ground as Meerkat has, we will then start the process of integrating Meerkat into the SKA systems. That is, we'll be connecting Meerkat antennas into the SKA digital systems and taking control of those antennas. So there has been a lot of thought and a lot of detailed planning about how that might happen, but it's some way down the line yet. It's Meerkat will be able to deliver a fantastic science program before that integration happens.
Yeah. We have time for maybe one more question. From Jacinta Del Hayes. She says, hi Phil, are there still plans to outrigger stations in other African countries in phase 2?
Yeah, hi, back to Jacinta. Yes, phase 2 is still our long-term aspiration. I call it the full SKA. And what I find gratifying is that several of our partner countries are very keen on moving forward to the full SKA once we've demonstrated that we can build SKA phase 1 and of course can operate it. So yes, those plans are still there, but it will cost a lot more money than SKA phase 1. So there'll be a significant program of work with the various partner countries. We will require more partners to join the collaboration, but that is the long-term aspiration: is to spread SKA phase 2 across Southern Africa and across Western Australia.
Fantastic.
Thanks.
We actually have time for one more question.
We have a question from Robin Catchpole, who asks, how much would you have to extend your diesel solar power system to make a useful contribution to the local community?
That's a question I haven't really considered. In fact, in Western Australia, there is not much of a local community. There's a small Aboriginal settlement, but that is actually being supported in terms of renewable power by the Western Australian government. That's about 90 kilometers away from the site. In Southern Africa, I think I'd pass that question to one of my South African colleagues to answer. It's not something that I've put much thought into, I'm afraid.
Yeah, I'm sure we can follow up on that later in the week. Thank you again for your talk. We're really looking forward to having the SKA here. It's very exciting.